Hello. In this video, we're going to walk through a sample 01 knapsack problem and solve it using OR tools. The goal here is to identify the optimal solution using the mathematical model, and then in the following video, we'll revisit the same problem, but this time we'll approach it using genetic algorithm and focus specifically on how constraints can be handled in the genetic algorithm framework. Moving on to the knapsack problem. It's a classic problem in operations research. Let's take a quick look at the problem. Let us say that we have a knapsack with a fixed limit with regards to the weight it can carry. That limit represents the capacity and we cannot exceed it. Now, suppose we have a large pool of items in front of us, 1500 items in our sample example, and each item has two attributes associated with it. First is the weight, which tells us how heavy that item is, and second is the value, such that a higher value is better. Now, our objective is to select a subset of these items such that the total value is as large as possible, while obviously ensuring the total weight does not exceed the knapsack's capacity. And the 01 part means that we can either pick an item or not pick it. So we cannot pick a fraction of any item. Now let's move on to the sample problem, starting by loading the pickle file. It contains the weights and values for all our 1500 items stored as a numpy array. Before going to the modeling part, let's look at a quick scatter plot of weight and value for the said items. Uh, the points are color coded by value per unit weight, which tells us kind of how efficient each item is. Taking a quick look at this shows us that the items near the top left seem like good candidates to pick. They are light and have a much more higher value per weight, while items towards the bottom right typically seem like a poor choice. Let us now take a look at the mathematical formulation, starting with the objective function, that is to maximize the total value of items we select. Mathematically, this is written as the sum of VIXI, where Vi represents the value of item I and Xi is the binary decision variable. If Xi is 1, it means that we selected that particular item. If it's 0, it means that we didn't. So when we sum over VIXI for all items, we are effectively adding up the values of only the items that were selected. The summation goes from 1 to n, where n is the total number of items. And this is subject to the capacity constraint, where we require the sum of Wixi to be less than or equal to C, where Wi is the weight of item I and C is the maximum capacity of the knapsack, and Xi again is the binary decision variable. In simple terms, this constraint ensures that the total weight of all selected items does not exceed what the knapsack can carry. As I mentioned earlier, the decision variable xi can only take values 0 or 1. Now let us implement this formulation using OR tools. Let us begin by assigning the weight vector, the value vector, and the capacity of the knapsack. These are the inputs to our optimization problem. Next, let us import the constraint programming module from OR tools. We'll be using the CPSAT solver. This solver is designed to work with integers only, which makes it a perfect fit for our problem since all of our parameters are integer valued. We then create an empty model. Before adding constraints or specifying the objective, let us first store the number of items in a variable. Next, we create the decision variables. These are the xi variables, so we'll have 1500 boolean values, one for each item. Each variable can take a value of either 0 or 1, indicating whether the corresponding item is included in the knapsack. With the variables defined, we add the capacity constraint. Summation wixi must be less than or equal to the knapsack capacity. After that, let's define the objective function. Uh, and our goal is to maximize the summation vixi. Now the model is defined, we initialize the solver instance and call solve, storing the turned status in the result variable. In this case, the solver has returned a status code of 4. Let us check what this corresponds to. So it means that the solution is optimal. Next, let us extract the selected items by checking which decision variables were set to 1. Let us now look at the total weight and total value of the selected items. As expected, the total weight is in accordance with the knapsack capacity. Finally, let us visualize the selected candidates using a quick plot. This will help us see how the chosen items are distributed in terms of weight and value. And that brings us to the end of this video. In the next one, we'll discuss the same problem using genetic algorithm and explore how constraints can be handled in that framework. Thank you.